Okay, so we looked at the case where the base was greater than 1 and it was an increasing exponential function. We looked at a couple of those. Now we're going to look at when the base is between 0 and 1. Just a note here, this is really important to note. We're going to categorize these bases as 0 to 1 and they're all going to act kind of similarly. But it's important to note that there's an exponent property. You got to really know your exponent properties. Any base to a negative number is the same as 1 over that base to the positive, okay, which can be written as that. Okay, so I have I picked 1/2 to the x for the example for base less than 1, but it's very important to note that 1/2 is the same number as 2 to the negative 1. And 2 to the negative 1 to the x, another exponent property, you'd multiply those guys, is the same as 2 to the negative x. So you'll see both of those. So even though now that I wrote it like this, it's the base is greater than 1, but the exponent's negative. But that's the same as the base less than 1, exponent positive. So you got to kind of pick one to do the second category. It's going to end up being a decreasing function. I'll show you how. But either way, they're the same thing. Okay, so just notice that, make a note that base less than 1 to the x, same thing as base greater than 1 to the negative x. Okay, so real quick, if we did this, I would pick some values for x, and I pick some values for the output, or I figure out what the output is, and I'll use the same one, -2, -1, 0, 1, 2, see what happens. So either case, so if I plug in -2, what's 1/2 to the -2? Well, that should be the same as, you don't have to do both of these, 2 to the -2, right? These are the same. A negative exponent means reciprocate, so that's 2 to the second. And these would cancel out, and that's also 2 to the second. So just to show you that they're the same, 1/2 to the -2, or 2 to the -2 is 4. 1/2 to the -1 is 2. 0 to the 1/2, that's still 1. 1/2 to the first power is a half. What's 1/2 to the second power? That's 1/2 times 1/2, or 1/4. Okay, do you see what's happening here? Input 0, output 1. And then it's kind of reversed, right? Input -1, output 2. Input -2, output 4. Input -3, which I don't have, the output would be 8. And then as I go to positive infinity, what's happening? I get a decreasing values, okay? So you have a very similar looking function, but it's reflected around the x-axis, and that's called exponential decay. And we could categorize this. We still have the intercept at 0, 1. We have it decreasing now. We have all the range. I didn't talk about that before. That's important. The range of this is 0 to infinity, never hitting 0. The domain, I can plug in anything I want, -infinity to positive infinity. That's the same for this case as well. Domain and range are always the same for your basic exponential function. Okay, this one's decreasing, this one's increasing. That's my two categories. And then we can do a couple transformations. If you remember that, that's not part of this pre-calculus course, but I'll link to some videos for review if you need it. There's some transformations that we do. This is a reflection around the y-axis. I'm sorry, the x-axis, if you replace x with -x. And this is a shift up 3. So this takes my graph that I just did, which looks like that, and reflects it around the x-axis. So it actually, let's use this color, makes it an increasing function. And then the +3 moves it up 3. So we had an asymptote at y equals 0. So now 1, 2, 3, my asymptote, horizontal, is y equals 3. And my graph would be this guy. Okay, that's just a real rough sketch. Real rough sketch of that function. We could do a little better if we had some points. This would be the point. Sorry. Going on with my pen here. This would be the point 0.4 instead of 0.1. This would be the point 1.5. Oh, I know why it's doing that. Let's fix that. 0.4 instead of 0.1. 1.5 instead of 1.2. And then that should have been 1.2, and then 2.4. That's a little off. The purple should be here, and then we're moving up 3. 1, 2, 3. So there's a little bit better graph of my transformed function. Okay, how about this one? Review of your transformation. So this takes this graph, and this is a shift to the left, so it moves it left 1. Sorry, right 1. It's backwards. So this takes 3 to the x and moves it right 1. And what's the 2 do? That's a vertical stretch. And I'll put a link in the comments of this, or the notes of this video, if you need a review on these different transformations. We basically have a left-right shift. You have a vertical stretch or compression based on the number multiplied, and you also have some reflections. Okay, so if you need a review on that, I'll post a review in the comments. For this one, we go right 1, and then this is a vertical stretch of 2. So here's my original function. I like to graph a couple points here. That's 0, 1, and 1, 3. That's 3 to the x. We're going to move it right 1. Well, yeah, let's move it right 1. So there and there. This is 3 to the x minus 1. And then we're going to stretch it by a factor of 2. So all my outputs get multiplied by 2. So that's the point 1, 1. That's the point 2, 2. Oh, it should be 2, 3. 1, 2, 3. Yeah, 2, 3. And then these get multiplied by 2. That's what this transformation does. So I'm going to have 2, 6, 4, 5, 6. I'm going to have 1, 2, 1, 2. And it's going to look something like that. Okay. So just graphing exponential functions. I mean, the basic ones are really easy to graph, right? If I just say graph this, that's your basic function with just the base and the exponent. Or if I say graph this, they fall into 2 categories. This one goes increasing. This one does decreasing, right? And then we add a couple transformations on those. Okay, let's take a look at our first application. I had a money application to start with. We had an initial amount of 10,000, and then I said 1 plus the rate if it was just once a year. In my initial video, that was 5%, and then raised to the t. We can apply this a little bit to a more realistic situation where you get interest. Usually interest is paid at the end of every month. So you would pay the interest. So you break up your rate in the interest over the years. If it's 12 times a year, like monthly, then you would take your 5% rate and divide it by 12 and apply it as you go through the year. And then that requires a shift to the exponential piece where you multiply by that number n times t. And you get this very famous formula, compound interest formula. Okay, your amount at time t is your principal amount, how much you invest initially, times 1 plus your rate, divided by how many times it's compounded a year, times that number to that number times t. Okay, pretty easy. What am I going to do with these? Oh, these are easy. If you can use your calculator, you can do these problems. All right, exponential functions. Application, a basic application. Suppose you invest $1,000, interest rate 5%, it's compounded monthly. That means n equals 12 for 3 years. All right. So my amount at time t, I can say it's a function of t, is 1,000 times 1 plus the 5%, always as a decimal, 0.05, divided by monthly, that's 12 times a year, to the 12 times t would be my function, input t. All right, but in this case, they're giving me a value for t, so I say, oh, t is 3, so I can plug in my input variable. This is a function of time. The other values are called parameters. This is the input variable t, and it's 3. Okay, so let's see. If I run that through my calculator, I should get, give me 1 second, I didn't do this ahead of time, but it won't take long. I always get this question in class, what do I do first? Well, you always work with in your parentheses, so get a value for that. If you get good with your calculator, if you have one of those nice graphing calculators, you can kind of plug it in all at once. But if not, you got to be careful with your order of operations. So if you want, I would do 0.05 divided by 12, that's 0.0041666. So if I want to, I could write each step, to be careful, 41666, and I won't round that much until the very end. I'm going to raise that to the power of 36. And I get 1.16. Again, you don't need to do all of these steps if you're good with your calculator. 1.16147, and then I multiply by 10,000. 1, 2, 3, 4. So I get 11614 and 70 cents. And you might have a little different answer if you round it differently. Okay, so that is how I do the basic compound interest formula. Just plug stuff in. Okay, what we want to do is investigate this in the next problem. We're going to see what happens if I just keep compounding higher. And we're going to come up with a really interesting result, one of the most important numbers in math. And we're going to see where it shows up naturally. And I'm talking about the number e. Okay, and this is going to be really important for us for our exponential functions going forward, because we're going to use this all the time. So in the next problem right here, in the next video, we're going to see how this number naturally arises in one example.